Hey, how's it going, guys? This is part 4 of my Gregtech 6 Fission Reactor tutorial series. Last time, we went over molten thorium salt and how you can use that in a reactor design. We went over more advanced reactor control mechanisms. We went over the burner reactor design and how it's an alternative to the breeder reactor in order to generate more advanced nuclear materials. And we briefly touched on the final tiers of fuel rods. In this episode, we're going to utilize those final tiers of fuel rods to make some low power and high power designs of reactors. We're going to go over some reactor automation, namely how you can insert and extract rods to and from the reactor. And we're also going to go over some more practical reactor designs, both large and small, in order to generate different types of power around your base and how you might want to incorporate those into your base, not only for your normal power generation, but also to provide different power types to different processes around your base. Let's get started with discussing how we can automatically insert and extract items to and from the reactor core. Now, there's one fundamental rule that you need to keep in mind when you're doing this kind of automation, and that is that the reactor core has to be off when you try to manipulate the rods inside of it. Now, to insert items into the reactor core, you have to actively push them into the top. So that means that you have to use something like a hopper or a hopper into an item pipe in order to push things into the top. So let's put a hopper here, and we'll put some reactor rods inside of it. And you'll see that currently nothing is happening, and that's because the reactor is on. If we turn it off, you'll see that the reactor rods got inserted. Let's turn this back on now. To retrieve items from the reactor, you have to pull them from the bottom, again with an active method like a hopper. So let's put a hopper on the bottom, and we'll point it this way, and you'll see again that nothing's happening, and that's because the reactor is currently on. If we turn the reactor off, you'll see that the rods get extracted from the reactor. So being able to automatically insert and extract rods from the reactor core using hoppers like this is pretty useful. But specifically, this bottom hopper is going to introduce two major sources of limitation to our automation system. The first limitation is that the hopper at the bottom is just going to immediately extract any rods that are inserted into this reactor. And we can demonstrate that by just putting a bunch of reflector rods in here. And you'll see that this bottom hopper is immediately sucking out all of the rods and throwing them on the ground. As you can imagine, we don't want that to happen when we're trying to automate this. The second limitation, which is tied into the first, is that this system does not allow us to preserve any kind of orientation inside of our reactor. It's not going to let us insert rods into any specific slots in the reactor, and it's not going to let us extract rods from any specific slots in the reactor. And if you remember, the reactors are very dependent on the adjacency of rods to each other, and we need to preserve that kind of pattern when we insert and extract our rods. So how do we deal with this? Well, we're going to do this by using different kinds of item filters. And I'm going to demonstrate a couple of different ways that you can do this because there are a couple of different options that all pose their own benefits and downsides. So the first way that I like to personally do it is through the use of item retrievers. So let's put a chest here, and we'll get some brass item pipes, and we'll just hook them up directly to the bottom of the reactor like that. And then we'll put the retriever cover on the bronze chest here. And let's say we want to only extract reflector rods. Obviously, in a real reactor, you would probably extract only spent fuel rods, for example. But just for the purposes of demonstrations, we're just going to use benign rods. So let's filter on the reflector rods, and we'll have this system dump in a bunch of reflector rods. And you'll see that those reflector rods do indeed get yanked out and put into this chest over here very slowly. Now, let's put some empty reactor rods in here. Let's put 2, for example. And you'll see that those 2 regular empty reactor rods are getting left inside of the reactor, and only the reflector rods are getting sucked into that chest. So you can see here how you can start to throw together a sort of filter to only extract the rods that you want to extract from the reactor. The second way that we can extract rods from the reactor core is through the use of compact robot arms. Now, there's quite a few of these available, and they're really not all that different from each other. They just cost different materials, and they extract at different rates. But realistically, any of these is suitable for a build like this. So just use whichever one you feel comfortable spending the resources on. Now, these are quite different from the way that retriever covers and hoppers work. And that's because compact robot arms will only extract from a specific slot on whatever inventory they're attached to. So in the case of the nuclear reactor, they only pull from one of the 4 slots that the rods go into. So how do we get this set up? First, you're going to put the compact robot arm on the side or the bottom of the reactor. You could even put it on the top if you wanted to, but I wouldn't recommend doing it like that. So let's just put it on the side like this. Now, to get it to pull from a specific slot, we're going to shift right-click with a screwdriver and have it cycle through the 4 slots of the top of the reactor. And those are going to number from 0, 1, 2, and 3, facing north. So you'll see 0, 1, 2, and 3. And again, that goes top left, top right, bottom right, facing north. So that's how you know what slot it's configured to. So slot 3 is going to be the bottom right. So we should see, if we fill this up with rods, that bottom right slot gets ejected, and indeed it did. And if we put a chest there, instead of getting thrown on the ground, that rod will instead get ejected into the chest. It'll just take a moment because this one doesn't extract that quickly, but you'll see that the rod is now in the chest. Now, if you do this on the side of the reactor, you have to immediately put an inventory next to that robot arm. If you were to put this on the bottom instead, you could use item pipes, because item pipes only connect to the bottom of the reactor. So if we instead put a robot arm on the bottom like that, and we configure it to say slot 0, and then we put a item pipe there, and we put a chest here, you'll see that slot 0, which is that top left slot, gets extracted, and you'll see it goes into the chest if we put another rod in there. So let's put it there. And momentarily, you should see that rod gets extracted by the robot arm and thrown into this chest. So you can see it's quite different from the way that the retriever cover works, because this one will only pull from one specific slot, but you can start to see how this method might allow you to preserve the orientation of your rods and do it in a way that you don't have to filter on a specific rod. Another way that we can automatically extract specific rods from the reactor is through the use of hoppers again. Now, this is pretty basic. It's not going to allow you the flexibility of doing it like the retriever or with the robot arm, but it will give you a basic filter that you can at least set to one type of rod so that you can at least extract whatever you're currently using in your reactor core. So let's put down a hopper, and on top of that, we'll put an item filter. And let's set that filter to the neutron reflector rods, and we'll point the hopper just to the right so that whatever gets extracted gets dumped on the ground so we can see. And then we'll put the reactor, and we'll turn it off, and then we'll put some reflector rods, and you'll see they get extracted. But if we put empty reactor rods, you'll see that they get left in while the other rods get removed. So the reflector rods that we filtered on get removed, and the empty reactor rods that we didn't filter on will stay in. And with hoppers, and specifically with filters, you can invert them to whatever you don't want them to remove. So say we wanted to keep empty reactor rods, but any other kind of rod we want to remove from the reactor. So let's set this to empty reactor rods, and then we'll take a screwdriver and we'll set it to blacklist. And that means that anything that is not the empty reactor rod will get extracted from the reactor. So let's point that again to the right. We'll put the reactor here, and we will turn it off. And then let's put the empty reactor rods. And if we put reflectors in, you'll see they also get removed. And if we took something like a breeder rod, for example, and let's just, for example, use a thorium breeder rod, you'll see that that gets extracted as well, because it doesn't match the blacklist filter that we put on the hopper. So again, the blacklist filter will extract everything that is not the thing that you set it to. Now that we know how to automatically remove specific rods from the reactor, we can start to discuss how we can solve the issue of preserving the orientation of the rods in the reactor while we're dealing with automation. So let's say hypothetically that we have a reactor that runs on plutonium-244. And what's going to end up happening is this reactor is going to consume that fuel rod eventually, and that fuel rod is going to turn into a depleted plutonium-244 fuel rod. So what we want to have happen is for the automation system to remove any depleted rods and then to refill the reactor with fresh fuel rods. So let's first set up the removal system. So we're going to set up this retriever cover to remove any depleted fuel rods. So we'll set that filter here, and we'll test that that's working by putting a depleted rod in the reactor core. And you'll see that it did indeed get removed from the reactor. Now, what we want to have happen next is for the fuel rods to be automatically refilled inside of here. So let's first set up the configuration that we might see in the real world. So let's have 2 reflector rods go here and here. And what we want to have happen is for the automation system to put a fuel rod here, because hypothetically in this situation, we might end up having some reactor cores that are adjacent to this one in this kind of configuration. And we need that specific slot to be filled so that it can interact with those other reactor cores. So let's set up a way to refill this reactor core with a hopper and an item pipe. Now let's put in some fuel rods and see what happens. You'll see that the slot that we didn't want to have filled in this top right, or rather the top left corner, ended up getting filled with a reactor rod. And we don't want that to happen in our setup, because hypothetically, our setup is only designed to run on a single fuel rod. So how do we solve this problem? Well, the way that I like to deal with this is by simply using an empty reactor rod and filling any unoccupied slots in the reactor with those empty reactor rods. So if we put one here and then we remove this rod and then put the item pipe back and hook it back up to the hopper, and let's put some fuel rods back in here, you'll see that now only this slot can be filled because it's the only one that has a free space. Now, just to quell your concerns, empty reactor rods don't interact with the reactor or any of the rods inside of it. So it's the perfect rod to use for this kind of situation where you need to fill any unoccupied slots so your automation system doesn't interact with them in any way. And because nothing can remove that reactor rod because we have all of our filters set to only extract depleted rods, what ends up happening is that now, whenever this rod depletes, we can turn the reactor off through some sort of automation, and then the retriever cover will pull the depleted rod out, and then the insertion system will put in a fresh rod. So this is a perfectly valid automation system for automatically refilling and extracting things from your reactor. Now, we can do the same exact system with a hopper. Instead of using the retriever cover, it's just that the hopper will have a filter on it, and it'll go in this slot here, where this item pipe is, rather than having the retriever on the chest. Either way is perfectly valid, and they'll both work exactly the same way, so you don't have to worry about that. With the robot arm, obviously you're going to have the robot arm removing from a specific slot, so you don't have to worry too much about removing things from the wrong slot. But again, inserting things if you don't have these slots filled is going to be a concern. Now, there's another way that we can refill the reactor and only fill specific slots, and I'll show that to you here. So what we do is we put some reactor cores, and let me just turn that so we can see what's going on in the reactor. And let's put a robot arm on the side of the reactor. Now, just as a note, normally you can only insert things into the top of the reactor through automation like a hopper or an item pipe, or even a retriever if we put the retriever on the reactor. But through the use of robot arms, we can actually use any side, even the top or the bottom, to insert things into the reactor. So what we want to do is we want to first set the robot arm to insert things into the reactor. So we take a monkey wrench and we right click on the side with the robot arm on it. So it has these blue arrows pointing in. That means it's going to insert things from this side into the reactor. Now we take a screwdriver, and instead of shift right clicking, we're going to right click to set whatever slot we want to put things into. So again, the counting starts from 0 and it goes from 0, 1, 2, and 3. And those represent the 3 slots. You can see puts into slot 0, puts into slot 1, 2, or 3. And those again correspond to top left, top right, bottom right. So let's say we want to put things into slot 3 and only slot 3. So let's put our reflector rods here. And this time we're going to leave this empty slot here just so we can demonstrate that the robot arm circumvents this issue. So let's put a chest here. And we'll put some plutonium rods here. And in 1 second, we'll see that this slot will be filled by the robot arm. And you can see, indeed it did. And if we remove it again, the robot arm will put a brand new rod inside that slot. So you can see that this provides an alternative to the system of using the empty reactor rods to insert things in. Personally, I prefer to just do it with the item pipes for one of several reasons. The biggest reason is that I like to be able to see what's going on with my reactor. And what ends up happening is that you end up occupying slots of the reactor, or rather sides of the reactor, with robot arms when you could really just leave those slots open for other things like universal extenders and pipes and other such things. And I just think it is nicer to have the things be inserted in a dummy fashion through the top of the reactor rather than having the robot arm. The other reason that I don't like to use robot arms for this is because they are kind of annoying to craft, and I just prefer to do it this way because, item pipes are cheap, hoppers are cheap, and once you have the empty reactor rods, it's really just easier to kind of filter into the slots that are empty. But, you can choose whatever method you want to do. But this is a valid way to do it, and likewise, the dummy method is valid. But these both represent ways that you can fully automate the insertion and extraction of things into the reactor and from the reactor in a way that you can control exactly what slots things are going into and coming out of. Now that we've reviewed all of the components of item insertion and extraction, we can start to look at how this is going to work in a real reactor. If you look over here, I've already completed a very small demo build of a burner reactor. Now, if you remember from last time, a burner reactor is a way to rapidly deplete your fuel rods, and I'm using this more so to demonstrate just the mechanisms of insertion and extraction. It doesn't really matter if you do this with a burner reactor or a breeder reactor or anything else. It's more so just for the purposes of demonstration. And you could see actually one of our fuel rods just got extracted, and we'll go over how it can actually be reinserted afterwards. But essentially, this is a standard burner reactor, so we just have 2 reactor cores here. This reactor core is full of rods, so that's an empty reactor rod. There's reflectors, and a uranium rod was here before, and this reactor core just has a reflector rod. And we're using universal extenders and sensors just like we would with any other reactor. And the hot coolant is being output at the bottom here, and it's going through this pipe, and it's going to this multi-block here, which we haven't seen before. So what this multi-block is actually just a heat exchanger. It's a multi-block large heat exchanger. Now, it does exactly the same thing as the heat exchangers we've been using thus far. So exactly like the tantalum heat exchangers, for example. The only differences are that it's a multi-block one, obviously, and it's also able to handle a significantly higher amount of heat. So if you look, this thing can output 16,384 heat units per tick. So if you remember, neutrons directly convert to heat. So we can max out this Geiger counter sensor in normal mode to basically 10,000 neutrons, and we'll get 10,000 heat units coming out of this heat exchanger. Now, the other difference is that this heat exchanger will output its heat into these heat transmitters, and you could hook that up to a distillation tower if you wanted to, or anything else that accepts heat. Here, I'm just using ovens so that you can kind of see when the heat levels rise and fall. But keep in mind, you can put anything here. You could put a large boiler or whatever you want that accepts heat. But I'm just using this so that we can crank our neutron count up so we can deplete those rods a little faster. So that is pretty standard over here. There's nothing too different from what we've already done before. But you'll have noticed that we have some redstone circuitry on this reactor that we have not gone over so far. So what is this all doing? Essentially, what we're trying to do with this build is have our rods inserted and extracted automatically with no intervention from us. So to accomplish that, what we really want to do is detect when our fuel rod has been depleted. And the case for that is going to be when that reactor core has no neutrons. Now, observant viewers might have realized that we could also hypothetically reach 0 neutrons if we turned off our reactor. And I'll go over that after we go through this circuit. But for now, just keep in mind, when the reactor core has 0 neutrons, that's when our fuel rod has been depleted. So we're detecting that case for 0 neutrons, and we're sending out a signal over here. And then we're also detecting when this reactor has 4 reactor rods in it, and we're sending that signal over here. And we'll go over what those signals are for in a moment, but I want to go over what these redstone components are actually doing here. Essentially, what those piston components are doing is creating redstone pulses out of a stable input. So essentially, say we have a sensor or even just a lever like here that's constantly outputting a redstone signal. Ideally for our circuit, what we want is just for pulses to come through afterwards. So we need to convert that stable input that would hypothetically be output when we have 0 neutrons, for example, and we just want to turn that into a very quick pulse so that we can process that pulse in a further circuit. So what we need to do is use this piston and this light blue concrete, and this could be any block that you can power, in order to generate a pulse. So what's going to happen is we're going to turn on this lever, and these 2 red alloy wires are going to be powered. And that's going to cause this concrete to become powered and then emit redstone to all the blocks around it. And then we're going to pick that up with a redstone repeater. But the piston underneath is then going to quickly update and push the concrete away. And what that's going to do is cause the concrete to no longer be powered because there's no redstone going into it. So the redstone output over here is going to turn off. And what that means is that we can turn a stable lever into a very quick pulse, which is exactly what we want for our circuit over there. Now, if you're playing with a mod like Project Red, this is available to you as just a single block kind of circuit that you can place in any orientation, and it doesn't require you to do all this. It's probably a little bit cheaper as well. So if you have this available, feel free to use this in place of this larger kind of contraption. Just keep in mind, this is available in vanilla Gregtech, and, you don't need to do anything fancy for it. So I just want to demonstrate that this is available, by default. You don't have to have any other mods, but if you do have this available, feel free to use it. It's much more convenient. And you can see it works the exact same way. They both do the exact same thing. It's just that this is a little bit more bulky. Now, the other redstone component I want to go over is this kind of little circular contraption here. What that does is actually stores a power inside of one of these blocks. And that might sound a little confusing, and I don't mean to explain it in that way. It's not actually exactly what it does, but it's easy to understand if you just think that there's a charge being stored inside of these blocks. So essentially, when you input redstone either into the blocks or into the wires here, it will cause the other side of the circuit to become powered. So right now, this block is being powered, or it was being powered by this lever, and therefore this redstone torch is now being turned off because this one is now on and it's constantly applying power to here, which causes this torch to turn off. If we were to apply power to this side of the circuit, which is this blue concrete and this wire here, the opposite will happen. So this torch will turn off, and then this one will turn on and hold that state in the circuit. So what this is called is actually a RS latch, and that means set and reset, or rather reset and set. And essentially, it just turns a redstone input into a sort of lever that you can control with redstone. So you can see if we pulse this lever, now the opposite has happened. This side of the circuit is now powered. And if we hit that lever, this side of the circuit becomes powered. So that just allows us to kind of switch a redstone signal back and forth across a circuit. And likewise with the pulse former, there is a single block version available in most redstone expansion mods like Project Red. So, if you have that available, it works exactly the same way. It just is available in a much more compact form. But we're going to use the full scale version that's available just with Gregtech and vanilla. So essentially what we're doing is we're detecting when the reactor has 0 neutrons, we're pulsing that signal into this set reset circuit over here. And then that is going to turn off the reactor by sending a signal through this concrete over to here. And what we're doing here is actually there's a, a redstone repeater on this piece of wire, which acts as a diode. And if for those who don't know, a diode is essentially a piece of circuitry that only allows electricity or charge to pass through in one direction. So the only way that redstone can flow through the circuit at this point is from the actual inputs from the reactor. So this lever here won't actually affect the circuit that's behind it. The only thing that can pass through here is either the lever going through here or the input that's coming through the repeater. So that means that we can control the reactor in addition to this circuit over here with a simple lever. But we can only do it if the conditions that we want over here are available. So that makes it much more stable for us. So it's not like we're going to have random overheat conditions. The reactor is never going to explode and evaporate all of our rods. This is a much safer way to build this design. So we have our redstone. It's only being allowed to flow through this direction. And when this circuit is on, it will disable the reactor because the redstone torch is on this side, which means it's on by default. But if it receives a charge, it's going to turn off. So essentially, whenever the reactor has 0 neutrons, the reactor is going to be told that it cannot turn on. It's going to be held in the off state. At that point, when the reactor is off, the item retrieval system can turn on. So that means that when we have a retriever over here that's retrieving depleted uranium rods, for example, that system can then retrieve the rods from the empty reactor. Because remember, you can only retrieve or extract items from a reactor that is turned off. So that's why we need this circuit, so that we can turn the reactor off in order to retrieve our empty reactor rods. So once that rod is retrieved, there's going to be an empty slot in the reactor. Now, if you remember, we're going to have a dummy insertion system with this hopper here. So we can demonstrate what's going to happen next by putting an item pipe on top, because if you remember, you can only insert like this through the top of the reactor, and we connect that to the hopper, and then let's connect the hopper to the reactor. And you'll see another rod was inserted, and then the reactor turned on automatically. So what happened here? Well, if you remember, we now have an itomometer sensor that's reading how many rods are in the reactor. And if there are 4 rods in the reactor, we're sending a pulse through this circuit here. We're changing the state of this circuit so that now the redstone is actually turned off here. So this block, this block is actually unpowered now. And that means that this part of the circuit is now off. And that means that this redstone torch can turn back on, which means the reactor can turn back on. So to simplify it, what we're doing is we're waiting for the neutron level to become 0, which means our rod is depleted. Then we're turning off the reactor so we can extract the depleted rod. And then we're waiting for a new rod to be inserted, therefore totaling the number of reactor rods back to 4. And then once that happens, we can turn the reactor back on and the whole thing can start over again. And this circuit will continuously run forever, and you'll never have to worry about doing anything except for supplying the uranium rods. Now, if you remember when I was talking about this at the beginning, I mentioned that there's another condition that can cause this neutron counter to read 0. And that's when you manually turn off the reactor yourself, for example, with a lever like this. So let's see what happens when we do that. So we turn that off, and this pulse guy just created a pulse, and it swapped this circuit here. If we turn this lever back off, you'll see the reactor does not turn back on. How do we deal with this? Well, there's a couple of ways that you can do this, but I find that the easiest way to do it is simply to put a button on this part of the latch, which is the RS latch, if you remember before. What this does is it swaps the position of the redstone charge in the circuit to the other side, which means that this is now going to turn off if we hit this button. So let's push that, and you'll see that it does indeed turn the reactor back on, and now the circuit is stable again, and it's holding its charge. You could do this by having some circuitry with this lever connected to this with a pulse former, sort of like over here. But I find that this actually gives you a little bit more control. It gives you an additional kind of parameter to turn the reactor back on when you manually turn it off. Just in case you ever make a mistake, it kind of causes you to think twice about what you're doing with the reactor before you officially turn it back on. But, if you want to, you could essentially just hook this lever over here with a redstone torch or a pulse former or whatever, just to give a quick pulse to this circuit to flip its state. It's really up to you. But like I said, I prefer when there's an extra additional input required to fully turn the reactor back on, because I find that when I'm doing maintenance on the reactor, I just want to double check everything before I fully turn it on, and it kind of requires you to think twice. But it's really up to you. This is essentially just the most stable and simple way that you can have this kind of control circuit. And you can see it's not all that complicated, and you could simplify it quite a bit if you have these redstone components like I mentioned before. And later on, if you have something like Open Computers or Computercraft, you can even simplify it further by having just a single block computer process all your inputs and then control the outputs. But that will be something that we can demonstrate later on. So we're getting close to the end of this part of the tutorial, but before we go, I want to review a couple of low-cost, low-footprint, and low-complexity uses for reactors that might surprise you in their usefulness and how you can integrate them into your base. If you remember, in the first reactor tutorial, we built this very small power-generating reactor using just the reactor itself, a steam turbine, and a dynamo, and we saw that you're able to actually create a good amount of power using just this, and your rod will last quite a long time, so this becomes almost a free source of power that will last you hours and hours of time. Likewise with this, you can actually generate pretty much any kind of power type in a very small footprint using a very small and uncomplicated reactor. So let's go over how we can actually do that. So for the first one, we're just going to go over heat units, which we've kind of been dealing with the whole time here. So we're going to put down a reactor here, and let's just put down the best heat exchanger we can put down that will fit in a single block, which is the tantalum hafnium carbide one. You don't really need this one, but I'm just going to do this for the purposes of demonstration and push this as far as I can get it. For the coolant, we're going to use industrial coolant, but you could really use any kind of coolant that will work in the heat exchanger. Just remember to check the stats of whatever you're using so you know how you're modifying your fuel. But for industrial coolant, we're going to benefit from an increase of the self-stat and of the emission stat. The only thing is that we're decreasing our factor, but we don't really care about that right now. We're just going to build a very stable reactor, and we're going to get the maximum amount of our lifetime out of it while still extracting a good amount of power. So let's put industrial coolant in here, and then we'll put a uranium-235 fuel rod in here. And then let's put a Geiger counter down so we can see what's going on inside of our reactor. Put it like that, and make sure we have this all set up. So we want both faces of the reactor to be pointing into the heat exchanger, and we want to make sure the heat exchanger is pointing into the reactor. And what this allows you to do is actually just pass the coolant back and forth between these two. So the hot coolant will come out of the reactor, go into the heat exchanger, and then immediately when the heat exchanger processes it back into normal coolant, it'll push it back into the reactor. So this is a very, very small infinite loop already of coolant, and we're only using 2 blocks here so far. Now let's turn this on, and we'll see that we get 128 neutrons right off the bat here. So if we wanted to just make use of this with just 1 fuel rod, we could generate 128 heat units, because remember, we're converting directly from neutrons to heat units with this kind of coolant. So right here, we could power any number of things that use heat. So we could use dryers or ovens or anything that requires heat units. You could even power a distillation tower just with this. And with the duration of the uranium-235 rod, which I believe is 10,000 minutes, you could basically power a distillation tower with nothing but a single fuel rod for essentially hours. I believe that converts to 300 hours of use out of just this one rod. If you wanted to, you could then put to use some of that automation that we talked about to just retrieve the empty rod and then refill it. So you could have an essentially infinite source of fuel, or as much as you really care to automate this, just powering a source of heat. Now, this is a 2-block wide setup, but if we put another reactor down here and we put reflector rods, let's get some reflector rods, we do this, we can actually extract a significant amount of heat out of this one fuel rod and not deplete its lifespan anymore. So you can see we're now getting 743 neutrons, which means we're getting 743 heat units out of this guy. And this can be used to power something really powerful like an extruder, for example, which are pretty notorious for using a lot of power and taking a lot of time. This would put you at, let's just compare it to the titanium extruder. This would allow you to use a titanium extruder, which would get you more than 6 times overclocking, I believe, on any extruder recipe. You just slap that guy on there, and then you would just put whatever you want to extrude in there, and you would have essentially an infinite source of extrusion power. And then you just turn this guy off when you don't need him, and then you turn him back on when you want the extruder to run. That's pretty impressive. And for just this tiny footprint, you could put this anywhere in your base to power anything that needs heat. Now, the really cool part is when I go into survival mode. And some of you might have already thought of the downside of this, or what you might think is the downside, which is radiation. So let's go to survival mode. You'll notice I am standing right next to this reactor, and I am not getting irradiated, and I am not wearing a radiation suit. So what this actually means is that until you pass a certain level of radiation, or rather a certain level of neutrons, the reactor itself won't output any radiation at all to its surroundings until you cross that threshold. So you could put this directly into the center of your base where you do all of your work, and you would be fine. Now, I've done a little bit of testing, and from what I've seen, the range for when it starts to actually output radiation into the world seems to be about 1,000. So when you cross the threshold of 1,000 neutrons, then the reactor will start to output radiation to its surroundings. But I've found that it's really not too bad even at that point. It tends to just increase by 1 or 2 blocks going past 1,000. So I think from 1,000, it's maybe 1 or 2 blocks, and then 1,500 is 3 or 4, and so on and so forth. But really, even if you just stayed below 1,000, you could power pretty much anything in your base that requires this amount of heat, which is a fair amount of things. You could power your crucibles, your extruders, dryers, ovens, pretty much anything that needs heat with just this, and you would never get a single bit of radiation on you. The only thing you need to keep in mind is that the reactor block itself does have radiation. Now, this reactor doesn't because it's just using a reflector rod, but this one does. So if you were to directly touch that reactor, you would end up getting some radiation on you, and then you would need to take a rad-away pill. But as long as you don't touch it, if you just put a block on top of it or something, you'll be completely fine. So that's one way to kind of more practically use a reactor without all of the infrastructure required to, automate it and, keep it cool and all that kind of stuff. This is completely stable. You'll get the maximum amount of lifespan out of your rod, and you'll be able to practically use this in any kind of setup in your base. Likewise, if we were to take away that extruder, we could put on a boiler here, for example, and then we would be able to run something with steam, which could be, a steam turbine, or it could be an autoclave even. And because the reactors are so easy to automate, you just put a redstone machine switch on this guy and you can turn him on and off as you need. It would be super simple to have a very highly compatible power source for pretty much any setup. And again, I really want to draw attention to just how compact this is compared to any other kind of setup. If you can imagine, how you would normally power most things, aside from maybe things that use rotation units, because usually with rotation units, you just use a diesel engine. But for things that usually take heat, just keep in mind the amount of infrastructure you need. On top of the burning box that you would usually use for heat, you have to pipe in fuel and you have to do all sorts of automation to control the burning box, turn it on and off rather, as you need it. For this, you just turn the reactor itself on and off. You never have to pipe in really any fuel. I would be surprised if you ended up burning out even one rod in a normal playthrough, especially if you use something more powerful than uranium-235. For example, if you use plutonium in this, you could get 20,000 minutes, which I believe converts to 600 actual hours of real life runtime. I would be very surprised if you ended up using up all of that. So if we put plutonium in here, you'll see we're already over 1,000. I believe this will put you into range of getting radiation once again. That's radiation there. But, if you stayed below that, if you were to extract this rod, you would get just straight up 500 neutrons, 512 neutrons, which is 512 heat units out of just a single plutonium rod. That's really impressive. And this thing, once again, lasts 600 real life hours. So, really powerful fuel source, really tiny footprint, just these 2 blocks, and you have potentially one of the most powerful heat sources with minimal effort. As long as you can refine and obtain these materials, you can kind of throw them wherever you want in your base. And again, as long as you stay below that radiation threshold, you'll be completely fine. So yeah, that's the last thing I wanted to draw attention to. And, use your imagination. You can really slot these into pretty much anything in your base. I really highly encourage people to not be afraid of these reactors. They're not that complicated. They're not that scary. The most you'll do is maybe irradiate yourself a little bit. If you die, you'll get rid of the radiation. If you take a Radaway pill, you'll be okay. They're really super convenient and they're extremely powerful, more powerful than people realize. So yeah, that's where I want to end this episode. And next time we'll go over some very complicated reactors. We'll do a full scale automatic breeder reactor that has all of the insertion and extraction mechanisms in it. I might even show some computer integration with open computers. And we'll show how you can actually generate massive amounts of power with these reactors, because so far we actually haven't really been extracting much power from these at all. And we're leaving quite a lot of potential on the table if we're only using these tiny turbines and these tiny dynamos. So yeah, next time we'll go over some more complicated reactor builds. But for now, I'll see you guys later.